If in the second case this heat transfer becomes equal, then it is steady state. Means no variation with time. We can give more examples like cooling of an apple in the refrigerator. So while it is cooling, its temperature is changing with respect to time. So it is transient or unsteady heat transfer process. In general, temperature changes position as well as with time in unsteady heat transfer process. Unsteady heat transfer process, like let's say this is some block, it's one point at 100 degrees Celsius A, and one this point at 50 degrees Celsius. So there is temperature variation with respect to position. And let's say we are observing at is at T1, and same block if we are observing at time T2, and same 2 points A and B, and if the temperature is changing, it means, so this is the point I'm trying to explain by this figure. So in general, steady state, steady state transfer can be um, variation of both function, both position as well as time. For one special case, in very special case, temperature can be function of time only for the case of lumped system. Lumped system. So in that case, we can specify a particular temperature of a body, particular temperature of a body at a particular time. So let's say same body as we have mentioned above. So it's, the size of the body and thermal conductivity and properties of the body is such that there is no variation of temperature with respect to position inside the body. So A, B, all positions have, let's say, same temperature at T is equal to T1. After some time, same point A and B is all such points. C, let's say 80 degrees Celsius, and all such points are have attained some temperature this at another time. So here we can see that there is no variation of temperature inside the body at every location, but there is variation of temperature with time. So this system is called lump system. So it means that here the material is cooling uniformly. There is no variation of temperature with respect to position. So most of the heat transfer processes we encounter in nature are transient. So we have to make assumptions to find the various parameters concerning about those systems. So let's talk about the multidimensional heat transfer. So we have studied about steady state and unsteady state. Similarly, this heat transfer can be one dimensional, two dimensional, three dimensional. So, heat transfer can be one dimensional, two dimensional, or three dimensional, depending on the relative magnitudes of heat transfer rates in different directions and level of accuracy we desire. In most of the engineering problems, heat transfer is generally three-dimensional. That is, temperature varies along all the primary directions within the body and during the heat transfer process, and also with time. So heat transfer in real applications are three-dimensional as well as unsteady. So let's say some of the problem uh, we can reduce to um, two-dimensional or one-dimensional, uh, depending on the variation of temperature. So like like plain wall, like wall of a room. Mm, so let's say all the points of the wall in vertical direction have same temperature, 70 degrees Celsius, and all the inside points have temperature of 80 degrees Celsius. So there is no variation of temperature with in y direction. Only variation is in x direction. So this problem looks like two-dimensional. And if we see the third dimension, then it looks like Z. So at every cross section, we can find the same profile at degree Celsius or degree Celsius at every cross section of the wall along the Z direction. So if it is same profile at every cross section, and if there is no variation of temperature in the y direction, and only variation is there in the x direction, as we can see here. So this is one-dimensional heat transfer. One-dimensional heat transfer process. Similarly, um, in most of the industrial pipes, and there is variation of temperature only with respect to R. So there is heat loss only in the radial direction. So temperature can be a function of R only, and the change of temperature with respect to the Z and the phi direction are neglected in such applications. To make the problem solvable. So as we have seen in the previous chapter about the Fourier's law. It is directly proportional to the temperature gradient. And so negative sign ensure that the heat transfer is positive, and heat is always conducted in the direction of decreasing temperature. And dt by dx is the slope of temperature profile in the body. So let's say this is the body, and this is the variation of temperature. So if we want to calculate the heat flux, heat transfer at any point in the body, then it will be then we need the slope at that particular location. Sorry. And in three-dimensional, we can write like this. This was for one-dimensional. Three-dimensional, we can write like q dot vector n. And this is obtained by imagining such thing. Let's say this is ether. It is transferred from here. So we can write like this each term. Kx, Ax, del Ty, del x. Similarly, minus Ky, Ay, Kz, Az, temperature gradient in y, temperature gradient in z. So for isotropic material, there is no variation of thermal conductivity or property of the material with respect to any direction. Kx, Ky is equal to Kz equal to K. K is function of temperature only for isotropic materials. For isotropic material. So from next class we will start the derivation of the heat conduction equation.